Hello, my name is Ben. I'm here to present my dashboard. So this is a dashboard for water quality in Uganda, and it's a presentation that's part of the course unit data visualization under the course Masters in Computer Science from the Makerere University. So let's dive right into it. So to begin with, I briefly go over the data set that I'm trying to visualize. So dataset appears in an Excel sheet. Um, as you can see, we have various sheets in here, and each sheet represents a district. And so these are districts from Uganda. And for each district, we have a column representing a different water source that was captured within that district. So water sources come from different villages, and they have a couple of attributes that come along with them, including the proportions of the water contents in different units, majority in milligrams per liter, at the different sources. At the extreme end here, we have the standard recommended values that are given water source, a given mineral content shouldn't exceed in order for that water to be classified as a good quality water. So these are sort of like the thresholds we use to determine whether a given content within the water at a particular source makes it a bad source. Yeah, so that pretty much wraps up what the data set looks like. So these are all various districts with all these attributes. Some of them are missing out on certain attributes. Yeah, but we're going to try and generate some visualizations for this data set. Yeah, so this is what the dashboard looks like. So first I have a general visualization of sort of to give an impression of how much each district contributes to the entire data set. And we can, yeah, so at this level, the circle packings, we have the several districts. So from here, we can see that most of the water sources are coming from Nomo because it has the hugest circle, and then followed by Kamuli, Luwero, Nakaseke. Generally, the sizes are giving us an idea of how much each district contributes to the entire data set. So we can go ahead and zoom in a bit to a particular district, for example. And when we zoom in, we can see the different water sources labeled by their names. And again, the larger the circle of a water source, sort of signifies the greater the values recorded for the different water sources, rather for the different minerals contained within the water that was sampled at that particular source. So for example, if I can zoom in here for this, we can see that this water source had a high concentration, high value for the calcium hardness as compared to other things like nitrate and sulfate and chloride. So we can generate like lots of information from this chart. So we can zoom out and maybe try out another district like Luka, and here we can see we have a couple components, and here sulfate is the most concentrated component per in terms of milligrams per liter of the water at that source. Yeah, so that's the first visualization. I mean, we can generate like lots of information from this. There's a lot to explore from this. So next, I have these sort of like visualizations that summarize what we have in the data set. So this is sort of captured in the circle packing, but it's hard to see or to tell from the circle packing. Which I mean, it's hard to look at the circles and tell that okay, Lamo has the the largest number of sources, followed by Kamuli. Like these circles are they're a bit hard uh, to interpret in terms of which one is bigger than the other. So for the interpretation of how many water sources are contained in each district, I resorted to generating a background. So this gives us an impression of how many water sources were captured from each district. So we can see here, Lamu was almost obvious from the circle parking, but for the next bit, for example, you see, you could hardly tell that Kamwenge has the second largest number of sources, more sources than Kamuli. So that's why this chart was necessary. So you can see that Kamwenge has the next largest number of water sources, followed by Nakaseke, and then the districts that recorded the least number of water sources were Bugeri and Mubende. These had only two. So for example, when we go back here, we see we have only two inner circles in Mubende, which are the two water sources from the villages Chenda and Chebando. So again, we can go ahead and sort of get an impression of the mineral contents per water source. Then the third visualization. So we have these samples were collected from various types of water sources. So we have this pie chart here that gives us an idea of what are the most common sources of samples. So we can see that most samples in the entire data set actually came from the borehole source type. And then we had other samples that were a bit they were a bit hard to sort of visualize within the pie chart on their own. So they were grouped together to compose this others section. Then we see wells also contribute a huge chunk, 27%. Unprotected springs contribute 16, sorry, not 27%, but rather 16 total water sources. And 12 total water sources were taps. And then we had one unprotected spring. So the fourth visualization here is a spider plot, and the aim for this was to sort of get an idea of how water sources from a single district compare with each other in terms of milligrams per liter for those minerals that are measured with those units. So here, for example, we can see that, sorry about this, we can see that in Mukono, for example, this orange layer on the radar, which is the Chiora village, had quite a large number of large concentration of sulfate and iron as compared to the others from the same district. So generally this plot could help with the analysis and easily spotting what mineral contents are abnormal, for example, as we might see in the near future when I move on to the next chart. So I can filter the different districts and see. So every time I filter, we overlay the layers of all the different water sources from the same district on the same radar plot, and we can be able to compare. So for example, here we see the percentage concentration of E. coli for the Busuna, this one here, the Busuna village is quite high and abnormal. So because the threshold for E. coli was about 0.01 milligrams. So if in this water source E. coli concentration is 50%, that means there's something really wrong with that water source here. So then the final chart, which was sort of like the ultimate goal, was it serves the purpose of, it visualizes all the different water sources on the Ugandan map. See, I can zoom in here. So the red sources, the red pins imply that the water at that source had something wrong with it in terms of the comparison between the value of a recorded a certain mineral content as compared to the threshold for that mineral content, as we're going to see. So if I hover over these sources, so the green ones are the ones that are okay. So when I hover, for example, here, maybe here, you see this was recorded for Uganda district, and from the Busei village, it's green, it has nothing wrong with it. So, but for example, when I come here, we have this green one, it's in Kamwenge and it's from village Kengoma. So it's green because the mineral contents from the proportions of the mineral contents are within the recommended values as per the threshold I displayed there in the Excel sheet I was beginning with the data set. So the red ones are the ones that have something, at least one mineral content that's going outside the recommended threshold. So for example, this one, we can see it's a source from Kamwenge still in a village called Chinyoza. And here we have an E. coli value of 3, which is greater than the recommended value of 1. Yeah. And then we have this one also, it's from Chinyoza, from Rutoma. It has an E. coli value of 4, which exceeds the recommended one. So that's why it's red, meaning the E. coli values in that water make it bad. And then, yeah, this is also in Rutoma. This is Chinyoza, and then yeah, these two are in Chinyoza. And then we have this one here. Kengoma 2 is the village, and we see it has a turbidity that is extremely high. It's 104, which exceeds the recommended value 25 by approximately 80 units. So that makes it a bad water source. So so maybe one observation we can see from here, we can see that we have another one here from Kamwenge still, and we can see again the E. coli value is greater than it's abnormal. It's 108. That's like too huge. So one observation we've made from this, we can see that most of the bad water sources in Kamwenge they're made bad by their value, their E. coli value. So it's something to do with E. coli. So maybe that would be an interesting point to begin with and assess why the E. coli values in particular, mostly the E. coli values are higher than the normal for the water sources from Kamwenge. So maybe if I'm to come here to the Kamwenge district, we can see that the E. coli values are quite enormous and abnormal. Yeah, these ones here. And then just to wrap up, so there's a lot of information that we can extract from this. So maybe if we move to the north here in Lamo district, so here the district, the story seems a bit different. So you can see that the different sources, there are most of the sources that are marked red, implying something is wrong with them. It's the alkalinity, the total alkalinity value that is going beyond the recommended value. So you see for this one, it's 444, which goes over the recommended 200. Here it's 264. So this sort of gives us an impression of what's going on here. You see, most of them have a messed up total alkalinity value. So we saw that in Kamwenge, the issue with the water sources was E. coli, and in Lamo now, the issue is total alkalinity mostly. So I guess this could also portray some information. And I believe there's a lot more information that can be done, can be extracted by going over these affected water sources and seeing which exact mineral contents are causing them to be categorized as affected water sources. Yeah, that wraps up the end of my presentation. Thank you for your attention. So maybe to wrap up, so these visualizations were all created using the D3 library from scratch. However, in order for me to have like this layout and for easy management of code, I use D3, but within the Vue.js library. So with Vue.js, I'm able to create every D3 visualization as a component of its own, and then I stack them up in a grid to present them on this single dashboard screen. Thank you.